And so now position, velocity, and acceleration are all vectors. Um, and you can make sense out of the relative motion equations if you think of it this way. So imagine two coordinate systems, A and B, with the same axis orientation. So the coordinate system orientations are the same. Each of these is tracking an object that I'll call O. Well, with one-dimensional motion, we were talking about two choices of the zero position, okay? And they had to be along the line because all the motion is along a line. But now what we're talking about is one coordinate system here that we'll call A, and that's the axis orientation. And another coordinate system here with the same axis, you know, the axes are in the same direction, and we'll call this one B. And both of them are measuring the motion of this object O. Let's think about the position vector as measured by each of these two coordinate systems. The position vector is always a vector from the origin to the object. So the position vector measured by A is this. So you can think of this as the position vector of O relative to A. And the position vector of O according to B is this. And notice that if you use A to measure the location not just of that object, but also the location of coordinate system B, you can think of this as the position of B relative to A, the position of B measured by A. And then what you see there is that according to the rules of vector addition, the position of the object relative to A is equal to the position of the object relative to B plus the position of B relative to A. Okay, all I'm doing is writing out the vector addition equation that you can see is clearly true from that picture. Okay, are you with me on that? And what we have is this is the same position relative motion equation from 1D. but now with vectors, now in 2D. And notice that the fraction multiplication memory device still works. The O over A is equal to O over B times B over A. So that's still a way to remember to get the order right. And now if these coordinate systems and the object are all moving, you can take the time derivatives of both sides of the equation. So d dt of both sides and it gives you the velocity and acceleration relative motion equations that we had in 1D. Just now everything is vectors. So everything works out the way that you would guess it would work if you had to guess. So velocity of the object relative to A is equal to the velocity of the object relative to B plus the velocity of B relative to A. And same with acceleration. If you take another time derivative, so the acceleration of O relative to A is equal to the acceleration of O relative to B plus the acceleration of B relative to A. And if it ever comes in handy, we also have these relationships for vectors. The position of, A relative to B is negative of the position vector of B relative to A. Same with velocity, same with acceleration. So if you need to switch those subscripts in order to make sense out of your problem, you can switch the subscripts, just multiply by a -1. So now velocity and acceleration. Okay. So this all works. I mean, you don't really have to remember a new approach or anything. We're just talking about things in terms of vectors now. All the rules with the subscripts that you did in 1D work in 2D. So let's see this work in 2 dimensions. So let's say that you're in a car. Let's make it a convertible so you can see what's going on. And you hit the brakes or run into something, and drop your coffee. Okay, let's see. Yeah, that's good enough. Okay, it's like a low rider. And meanwhile, while all this is going on, your kid in the back is filming it with your iPhone. Okay, so this is the coordinate system. The coordinate system is fixed to the car, moving with the car. The car's velocity is this way. If you slam on the brakes, what's the direction of the acceleration? Opposite. Okay, so let's say that the acceleration magnitude is, let's say 30 meters per second squared. That's pretty big, but let's say that's what it is. According to the camera, what's the acceleration of the coffee? Okay, so let's set this up as, so C is the coffee, G is the ground, not the coffee grounds, and I call it V for vehicle. But all these things are moving together. So V is the vehicle, the passenger, the camera. Okay. And we're talking about acceleration, so we want the acceleration equation. So the acceleration of the coffee relative to the ground is equal to the acceleration of the coffee relative to the vehicle plus the acceleration of the vehicle relative to the ground. And now we can start to fill in what we know. This coffee, once you let go of it, is in free fall. So if our coordinate system orientation has the y-axis up, then the acceleration of the coffee relative to the ground is 0, negative 9.81. Okay. Do we know the acceleration of the coffee relative to the vehicle? No, that's what we're trying to find, right? We're trying to find this camera that's mounted to the vehicle. What does it see for an acceleration? So if it measured a bunch of positions through that camera and then figured out a function and took time derivatives, we're figuring out the acceleration that it would think this coffee cup had. Okay, this is what we're looking for. Do we know the acceleration of the vehicle relative to the ground? Yeah, we're given that it has a magnitude of 30 meters per second squared. We know it's in the negative x direction. So this is negative 30, 0. And so now just solve for this variable. The acceleration of c relative to v is equal to add negative 30, 0 to both sides, subtract negative 30, 0 to both sides. It's like adding 30, 0. And you get 30, negative 9.81. meters per second squared. Okay, so that's why if you're driving in your car and you have something sitting on the console or whatever, and you slam on the brakes, to you sitting in the car, it looks like that thing flies forward, and it runs into the dashboard. That's not really what's happening to an observer that sees it happen from the side. If your car was glass and they could watch this happen, they would just see this thing once it fell, it would just accelerate straight down. It's in free fall. So that's what's happening to an observer that's on the ground. But to an observer in the car, and also that observer on the ground on the street watching it would see the car accelerate the other direction. It would be like okay, so let me draw this. So here's the coffee cup. And to an observer on the street who's watching this coffee cup, it would look like this coffee cup's going however fast, 30 miles per hour, horizontally. And then it becomes a projectile, and from that point on, it follows a parabolic motion like that, according to the rules of free fall. Okay? It wouldn't fall straight down in their view. It would be a projectile that started out at 30 miles per hour, but its acceleration would be straight down. And what that person would see is that the car would have a negative acceleration that pulled it out of this path. So the car would still be going forward, but it would be going forward more slowly than this as it came to stop. Okay. So to an observer on the street, the coffee is just in projectile motion. To a person sitting in the car, that's not what it looks like. If you actually measured everything out carefully, it wouldn't look to the driver like that coffee cup was in projectile motion. It would look to the driver like that coffee cup accelerated forward into the dashboard.